We'll start now. This is class number 5 of finite element methods, 23rd January 2020. From the last time, class number 4, oops, wrong course. We had done the problem that we use the quadratic interpolation function, which was constructed on the global coordinate. So we use the x coordinate in order to construct the shape functions, right? So you found that every time you move to the next element, you need to come back to reconstruct the functions, which is not so convenient for the finite element approach that you expect numbers of elements to improve the quality of your solution, to improve the convergence. So more elements, that means more operations you need to use for the basis function construction. So today we will bring you to the technique which is so-called isoparametric mapping. Actually, think about the mapping. So what is this mapping? This is a procedure that enable you to construct your shape function, which is actually for the calculation in your physical domain. So over here we call this physical domain, and this physical domain you use the global coordinates. Your global coordinate is in this shape, okay, x or y, but it is aligned with your global coordinate. Whereas so basically the global coordinates, you represent this in the Arabic letters x, y, z. Whereas the local coordinates, we use Greek letters. So we meet this guy. Your local coordinates is actually in the computational domain. Or numerical domain, and that requires the construction of functions in using the local coordinates, which is generally represented by the Greek letters. Like this. So they might not orient the same way as x, y, and z. Right. Actually, we used to do some of these things in computer method in structural analysis. So you know that the local elements, local member, the alignment or orientation could be whatever you want, but then we will perform some sort of over there we use direction cosine, right? And then we get the information from local coordinates back to the global one. So the degree of freedom, displacements, etc., okay, transform into the global one. Because the mapping is useful when you perform the stiffness matrix construction, those element things. But finally, you're gonna push everything back into the global coordinates for the overall system calculation. So we're here. Too big. Right. I put it here. Okay. So this is the mapping. It is a way that you match one point on the physical domain to the point on the numerical domain. So the coordinates here could be x. Oops. So x will be matched to the c. Okay. So your c values ranges. C is not just random. We have the fixed value of c, so it ranges from -1 to 1. X could be xi to xi plus 1, two different x values, right? The size of the parent element, it is given. When we talk about 1D, we talk about the length. When we talk about 2D, then the scaling is not the length anymore, it is the area sort of scaling, and then you're gonna learn about the Jacobian of transformation. Likewise for 3D, it is the scaling of the volume. Okay, so 1D scaling is the length, 2D scaling area and volume. So for 1D scaling, the element size h is just given by the xi plus 1 minus the xi, right? So this size is mapped onto this numerical domain element which has the size of 2. Okay. There's some reason why we use the c equals to -1 to 1. That is good for us to run the integration, to conduct the integration, because you know that everything, once it is transformed into the c, that will be stuffed into the integral. We will evaluate the integral like before, but we just change from one to another domain. That's it, right? Now let's see how does this mapping works. So to map, you need to be able to express the value of x in terms of c. Right. So x can be expressed in terms of c by x is equal to you look at this, you see that it should be xi plus c times h over 2, right? X equals to xi plus c times h over 2 and also plus h over 2. Keep in mind that your c value start from -1 all the way to 1, right? So if the value is here at the left point, it should be matching with this left point, so you drop in -1 there, you don't get the xi. You need to add up with the h over 2 for the fact that c starts from -1. Okay, so now you can establish these relationships between x and c. Now let's see the relationships between the derivatives of x and c. So if you take derivatives of this equation, derivative of x turns out to be the dx. xi is a constant value, you get nothing. C is c, so take derivative of c, you get dc h over 2, and the h over 2 on the back disappear. Or dc is equals to 2 over h dx. Now we try to express our shape functions in terms of c. Right. We establish these coordinates in order to make the shape function standard. Okay. We have the sets of standard shape function for linear and for quadratic, and then it will be used for trillion elements that you will have later. So it is reusable, it is universal. So let's take a look at the first one. So so at this point c equals to -1 and another point c is equal to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4. This point here, c is equal to 0. So start with the linear shape function. So you start with phi 1 and the other one is phi 2. Right now phi 1 is a function of c and it is given by the first point. This function passes 0 where c is equals to 1, so we're gonna have the c minus 1 term in there, right? But it is just one point that it passes 0. So if you drop in the value of c being minus 1, the requirement is that we're gonna get the value of 1 out of this function phi 1. So as you drop in, you get minus 2, right? Then you got to scale it back by minus 1 over 2. And for phi 2, not okay. Minus 1, right? Because it passes the 0 over there. So c minus 1, it is the c plus 1. You substitute the value of c being equal to 1 into here, you get 2. So you scale it out by 1 over 2. And likewise for quadratic shape function, so you have the same thing we saw previously. Okay, phi 1, phi 2. For quadratic, let's see, the first one, it passes c equals to 0, it passes c equals to 1. The next one, c passes 1, c passes minus 1, and the last one, c passes 0 and c passes minus 1, so it is like this. Substitute the value in. So this one here, you got to put the minus 1 and minus 1, you get minus 2, to minus 1 you get 2, so you scale it out this way. 0 and 0 you get minus 1, then you put the minus there, and then 1 and 1 you get 2, you get a half down there. So move to the next page. Your displacement u, which is approximate, right? This is the approximate finite element solution. So u will be given by, if you deal with the linear interpolation, you have u1 phi 1, but your phi right now is the function of c, u2 phi 2 and c, where 1 and 2 represent the the node in the local node number. Okay. Should move it down this way. You know, in the morning I was writing something on the paper, the real paper, and I tried to zoom. Well, these days I am using the pen just for giving someone signature. That's it. And I don't really write things on the paper. This morning I have to write the evaluation form something. So, it cannot be zoomed. Well. It is kind of cool to live in this age, to see the change of the world from the age that I use a lot of pencil and pens, a lot of paper, do all the calculations by hands. Well, I am just too young to catch up with the slide rules. Before the calculators, you got to use the slide rules, and that is the mechanical way of running the calculations. Okay, so I missed that age. And then first with experience the Windows 3.11. You never know that, right? Windows 3.11, Windows 4, and then it turns out to be the next gen is Windows 95, because it was released in the year of 1995, and the shape looks pretty much like Windows today. Windows 3, Windows 4 are totally different than Windows these days. And then Windows NT, Windows 2000, Windows blah blah blah, XP, Windows 7, Windows 8, all the way to now Windows 10. A lot of change. At the time that I have no idea that this thing would be possible to write on something electronically. At that, back in about 15 years, there was like the HP iPad, IPAQ. It has a pen and the palm size, pretty much like a mobile phone. At that time, what is it? Yeah, there's one brand called Palm, I guess. Many technologies, evolutions over this my entire life, to see things and to change. Use less paper, use more computer. Alright. For come back, linear interpolation, we expect to see more. I don't think it is quite favorable to see more change. Not so human friendly. So basically, interpolation function is cast using the local coordinates. This is the only change when you see the displacement u. So it is no longer the function of x, it is a function of c. And the thing that will change drastically, significantly, du d what? When you want to take this derivative, it is still the derivative with respect to x. Derivative with respect to x, well, if you look into the formulation, how do you compute derivative of displacement? You need the strain, right? Or you need stress. All those things are the real physical quantities. But you cannot just say that, oh, I'm no longer interested in the x. I'm no longer interested in du dx. I'll be just looking into du dz. Is that possible? It has no physical meaning. C is the assumed domain. So you don't really have a physical meaning from it. So when we talk about derivatives, we come back to du dx. So how do we calculate du dx? It is, right now your u is the function of c, right? So you're going to get a du dc. But what you learn from the chain rule calculus, right? You're going to get dc dx. Basically, for the u itself, well, I think one bad thing about using iPad to teach is that I can do this and you don't plan to do this if you use the paper. So you cannot just push it down like there. I'm not encouraging you to buy, but I'm just saying that I am sloppy, more sloppy. If I put it on the board, I cannot do that. So I got to be like consistent with the paper kind of writing. What you see that over here, it can be given in the concise form. So the expression can be given like the summation I equals to 1 to n, where n is actually just 1 or 2. Sorry, 2 or 3. Because we use all the way up to just quadratic. And then u I phi I c. Is it the same? Exactly the same, right? You just expand it, you get the form above. So this is just the compact form of doing things. So next, I can write the du dc in terms of summation ui. You differentiate ui, you get nothing. It's constant associated at a node. It is a variable that you need to figure out, but it is not the function. So we have ui and then d phi I dc. And then multiply by dc dx. Right now the dc dx is easy to find. Later, when you do the 2D, it's no longer easy to find. So it will be tricky in the future for this term dc dx. But for now, you can just come to this page and you see that dc dx is equals to 2 over h. So it will be funny when maybe in the next 30 years and then I look back to this course video and see myself using iPad. This is iPad Pro, which is so cool at that time. It will happen. It will happen. This will obsolete one day. But it will be interesting. What else? Actually, this might not be so useful for this sort of element now. If I want to express my x value being x1 phi1 plus x2 phi2. So my x is equal to, we are not going to use this expression here for the 1D element formulation. It is not necessary, but okay, 2D 3D you will like to express the coordinate x, y and z in terms of the local coordinates, and then you'll be able to identify the point inside, and you will use this function to compute the derivative and so on and so forth. You'll be using this component later, right? So x can be given this way, of course. Now we look at the derivative of shape functions. In local coordinates. So look at the first linear. Interpolation. Functions. D phi1 dc equals to linear equals to minus 1 over 2, and another is plus 1 over 2. Next one is the quadratic interpolation functions. So the quadratic, let's take a look. You'll be having a half c square minus c for the first one For the second one, you'll be getting c square minus 1 square, so it turns out to be 1 minus c square, right? And the third one, a half of c square plus c. So you take derivative, you get 2c minus 1 and 2c plus 1. 2c cancel out, 2c cancel out with a half, so we get the c minus a half. C what minus a half this one ends up, we will end up with minus 2c. Okay, looks good. So let us come back to the formulations. For example, if we are considering the same bar problem, so I need to, not this one, okay, copy this one, bring it there. So first, solving this problem, using linear element, I try to use most of these terminologies, so you can familiarize your ears with these words, and when you read the journals, any manuscripts relating to the FEM, then you can understand, oh, they are talking about this and this and this. There are so many terminologies. So we do the linear interpolation. We have element number 1, 2, 3, 4. The procedures. It's actually not changed. So first of all, your W is the function that looks like this, like before. So you have the integration I'm not including the boundary condition terms in here. You know how to fix them. But start from 0 to L over 4. Beyond L over 4, 0 elsewhere for the W value. So you will not include those range for the integration. You have the EA, the U, the X. It is not du dc, of course. dw, the X minus there and plus 0 to L over 4 F W dx equals to 0. Now we will substitute in, but let's look at this dx. We are going to change the derivatives into the function of c. Then you also have to change the domain of integration, right? So in order to do that, let's take a look. The domain of integration right now spans over the element. It is the dx, and we know that the dx is equal to h over 2 dc. So we are going to fix this. So dx is h over 2 dc. If you change the domain like this, that means you need to change the range of this integration. So x used to be in 0 to L over 4. So you'll be changing it into c, which is in the range of -1 to 1. The h here is equal to L over 4. Right. We learned here that the h is element size, so it is from this one here that you have for this case L over 4 minus 0. The second node locates at x equals to L over 4, and first node is at x equals to 0. So these are what we have to do. A couple things. Domain of the integration. This dx. After that, we are good to move forward. So oops, should it be next page? Yeah, good already. Next page. So this integral changes into this form from -1 to 1. The EA is still the same. Basically the EA can be the function if you want. So if you want the EA to start from 1 EA and then gets enlarged to be like 3 EA, you can write the EA as a function of x, right? And then you can convert from x to c later on. EA du dx, so I will come here and take the du dx. Look at this. Du dx is that summation. Okay, so du dx, first of all, you get what? 2 over h, because you have the dc over dx scale to that du over dc. Okay, derivative of u with respect to c, h over 2 here, I mean this part here, 2 over h, yeah. So I'm talking about this part here, 2 over h I put there, and then we need to write these terms next. 2 over h is there already, then I come here, derivative, right? U1, what is this? Linear, minus 1/2, and then plus U2, right? That's all. Multiply by the dw dx. So dw dx, again, you have this and this for dw, but it is with respect to c. To make it with the x, then you got to multiply by dc dx, which is 2 over h. So dw dx, I will put this bracket, so you're not getting confused. dw dx, the first w is minus 1/2, and then you multiply by 2 over h, right? dw dx, which is d phi 1 dc times dc dx, and this term is du wiggle dx, that is, okay, I don't need to explain, we talked about it already, don't expand it out. And then you have the what, h over 2 dz, h over 2 dc, and this one is dx. Wow, multicolor. When I was taking calculus 1, and in my first year in my undergrad, I had like 5-6 pens, pretty much like this. At that time, we need a pen, the color pen. And then end of this, pretty much close to the end of the semester, final exam is coming up. My good friend asked for my lecture notes, and I graciously I can give it to him. Okay, I'm okay. He opened it up and he said that, okay, this one needs a color photocopy. the black and white photocopy will not work. It contains like too many colors in there. Actually, I should look back into those books. I don't know where I keep it. It might be recycled already. It might be a good old thing to look back and see what I did at that time, at that age. You people these days, if you use the electronic pen, then it is just one, and then you just select the color. But at that time, you carry like a bunch of pens in the pencil box. Everything is here. Then we talk about this one from -1 to 1 as well. This force distribution is stuff in, and we need the shape function. You need a W. So W is the shape function number 1, a half 1 minus C. And on the back you need to change this domain. Equal to 0. The fun part will be coming up, but not bad. But you now see that the procedures, okay, the first set of equation you don't feel the pain. The second one you will not feel the pain. It sounds strange. You expect that the second one you will get the pain, but no, the second one you will not have a pain. And later on it is quite easy, because now you don't keep finding the new sets of shape functions. So you just pull it in here and use, pull it in here and use, and the thing that will be changed, which is u1, u2, u3, u4, but the function inside there is completely the same. So evaluate it up. Minus EA should be taken out. You have h over 2 and 2 over h, right? I will get 1 over 2, or 1 turns out to be 1 over 4. 1 over 2, I mean this and this. Okay, we're taken out. 2 over h cancel out with h over 2, so you have just 1 2 over h. It's not square up. So let me tick here, tick 1, tick out, and tick out, right? So I didn't bring out the minus sign, so the minus sign shall be minus, we will get the u1 minus u2, and as u1 and u2 are both not a function of c, u1, u2 has nothing to do with the distribution. The c takes care of the distribution, so you get minus 1 to 1. Practically we bring out every single thing inside this integral. I feel stressed and then I cannot write it down properly. Now let me check. Minus sign, this is all there. Minus, that clears out. I feel strange here. Do I miss any minus sign? No. u1 minus 1 over 2. Okay. Well, let's continue first and then we'll figure out that. I think 1 minus sign is missing from here. The thing is that if we move this to another side of the equation, it will be plus, and then we're gonna get u1 minus u2. Oh yeah, that is correct. Okay, all right, yeah, that's correct already. plus minus 1 to 1, and I will take fh over 2 fh over 2 over 4 to 4 fh over 4 1 minus c dc equals to 0. Now let's take a look at this thing. Integration of minus 1 to 1, if 1 dc, that's going to be equals to c evaluated from minus 1 to 1, which is equals to 2. If you evaluate c, then you get the c square over 2 evaluated from minus 1 to 1, which makes it 0. Next, c square, so this will be third q, makes it 2/3. And makes it 0. So you can see that if the power is the even number to the power, if the original power before the integration is the odd number, you're gonna get the square term or power of 4, of 6, of 8, and that's gonna make the minus 1 square and makes 1 square or minus 1 to the 4th and 1 to the 4th be identical. So the integral will give you the 0. So we look for the odd terms and then we just cut them out of the consideration. Even term, then you need to take a look at them. So this thing here will make 0. Over here is 2, right? So 2 cancel, 2 to 2 you get 4, and 4 cancel out, you get minus EA over H. Later on we will transform H into L over 4, and that solve U1 minus U2 plus this term you get 2, so you get FH over 2 equals to 0. EA over H, EA over L, right? It's like EA over the length of the member. FH over 2, a half of the load contributes to one node, another half of the load contributes to the right hand. So this is the tributary area concept when you use the linear shape function. That's it, you get the first equation. And then you move over to the second node. So to the second node, what is changed will be only thing that will change is the shape function here, that one over 2 is changed, and this one is changed. So this one is V2. Likewise for this one, 2. Nothing else change. So you continue the calculation. So basically I copy this. To here. And I'll just need to change a few things. First, plus, and then here minus plus. Right, that's all, right? Plus here doesn't bother. You end up with that minus EA over H U minus U1 plus U2 plus FH over 4 equals to 0, which is equation number 2. Basically it's not done yet. Okay, it's not complete. We have another part. Well, sorry. Yeah. So that's why I said another part. This one will be for the element number 2. We have integration from 0 to L over 4 previously, but now once you change the test function W to be associated with the second node, So you need to incorporate two elements. So this part comes in. So it's not like this. It is minus, this is u2 minus u3, and this term is negative. Okay, what else? I should just write it down this way, keep it small space. This is the integration from L over 4 to L over 2, which is a minus in here, dA du dx dw dx, and this is in element number 2. So the whole things come from here. Du, okay. So u in element number 2. No, this doesn't need to be changed. Sorry. Okay, this one, the sign here does not change. Sorry. Minus plus. Okay. And another thing is this term. Paste here. Oops, no space. Okay. This here we use this with the phi 1. Likewise for this one, it is the phi 1. The phi 1 stands for the phi 1 for local element. So here is what I mean. So this turns out to be the phi 1 for E2, and this is the phi 2 for element number 1. Okay, so pretty clear now. No, not bad. Copy, paste it. Thing is that well, the sign over here is going to change, and 1 is no longer there. So it is u minus 3. Everything is same. Okay, and down here take this and paste there. Change the shape function to minus, doesn't matter. So this and then minus EA over H U2 minus U3. Okay, so you end up with the form that looks like FH over what? This one, FH over 2, right? So get FH, and then here is a minus EA over H minus U1 plus 2 U2 minus U3. That's it. Equation number 2. 3, 4, 5. So just continue like this. So I don't need to elaborate more at other points. The operation will be just repeating what we just have done over these 2 points. Do we need another one? Yeah. Another one, you're gonna get the point force appear in this, and that's it. So we can move over to the quadratic interpolation. When we have 2-hour class, it feels like forever. Okay, quadratic interpolation, same problem. I keep the number of degree of freedom, maintain it. So we have element number 1 and element number 2. Okay, just 2 elements. So let's see the U for element 1. I'm not worried about the U, I worry about the du, dx, so we're gonna expand it out. Okay. Alright. So that is summation. Okay. U1 phi1 plus U2 phi2 plus U3 phi3, and the du dx is equals to U1 minus a half plus U2 times minus 2c plus U3 a half, like that. Right. As it is du dx, we need c over x, which is 2 over h. Okay. And element number 2, let us provide that's it. So we can start. It's gonna be longer. Integration from 0 to L over 2 minus EA du dx dw dx dx plus integration 0 to L over 2 f w dx equals to 0. Keep in mind that your h for this one is equal to L over 2, not L over 4. We don't have the same element size. So how does it start? 0. Minus 1 to 1. We change the domain. Du dx, then I take from here okay, just need to squeeze it in. And dw dx, so the first dw dx is the c minus 1 c minus a half times 2 over h right, and then the h over 2 dc. Okay, so this is dw dx, this is the x, this is the dx. Quite interesting. You can see the pretty much like a disaster awaiting. If your eagle eyes can see that this guy is gonna come to here, and come to here, of course, we are going to evaluate polynomials, the integral of polynomial by direct integration, and this is going to be the last time because it is painful. I know how to do it in the less painful way. Alright, and that's what people in finite element business like. Generally, this mathematical way, theoretical way to conduct integration you learn in calculus, friendly to you, not friendly to computer. If you write the code, ask MATLAB to conduct the integration like this, MATLAB can do. The point is that the operation takes so much time, and if you do it for millions elements, you take forever to complete the loop. So This is numerical method course. Finite element is the branch of numerical method. Then you be knowing the numerical integration, which is good for the domain from -1 to 1 like this, and it is also good for polynomial integration. It's not today, but I just tell you that this is going to be our last time that we integrate everything like this. The problem is that to do it in the conventional way, first you need to multiply this term and this term. Time consuming. This is the operation we don't like. If we use numerical integration, you don't need to multiply them. I mean, you do not need to come up with the closed form of like c square term plus something, c plus something there. You just keep it this way, and then you substitute value, some value into the c. So that depends on how many Gauss point you use. It is called Gauss quadrature. We're gonna learn that, but not today. Before we enjoy that privilege, we go through this pain, and the guy who go through this pain is me. I don't understand why. Next year it will be the guy on YouTube, not this guy. So pull out the thing that does not need to stay inside the integral. 2 over h over 2. So 2 over h was taken out there. The rest should be just these people. So start with U1. C minus 1, C minus a half times C a half, then you expand it up. I'm not satisfied with this C. Okay. C square minus C plus a quarter. The second term plus U2 C a half times 1 a half times 2C minus sign cancel out, and then minus 2C square plus U3 C plus 1 and C minus 1, you get C square minus 1/4 dC. The point is that we will first look for the way to make life easy. So I don't consider these two guys. What will I get from this one? Multiply by 2. This one multiply by 2/3. Right? Looks easy. So 2/3 multiplied by 2, you get 4/3. this 2/3 to 2, okay, 4/3, okay, 2/3, so sorry, we need to finish this up. Okay, 2/3 plus a half, 2/3 plus a half is 3, 2 is 4, right? 7/3. Not third, then 7/6. This guy is 2 to 2, 4, 4/3, or 8/6. Ơi. And the last one, last and least, 2/3 and then minus a half, right? So 4 minus 3/6, which is 1/6. If I just take the 2 and distribute it in, then it will be 3, 3, 3. Not bad if done systematically. If you just move forward, try to push without strategic thinking. So I will make it here minus EA/H multiplied by 7/3 U1 plus 8/3 U2 plus 1/3 U3. How about the first term? The first term is basically the plus minus 1 to 1 of F and W. The W is, let me check. Okay, so this one, a half C square minus C. Huh? U2 minus? Oh yes, thank you. So you integrate this term plus FH over 4 C square, you get what? 2/3, okay, multiplied by 2/3. That makes the FH over 6. equals to 0. Equation number 1. And have a bunch after. Your homework is to do it for I'm not going to ask you to run the whole thing, to use this one as the W and to use this one as your W. So when you use this one, then you'll be dealing with the displacement in the element number 2 as well. And just that, you don't need to use the W for U4 and U5. I just want you to try. That's it. So still bearable. Homework is not that difficult. So you don't need to ask your friend, and you don't need to copy, right? Or I will throw you the exam. Okay. Shall we? Let me see. Yeah, looks good. I think enough. So next time we come back and we will use the numerical integration. We learn about that concept, and you find that numerical methods is very beautiful. So once you learn numerical integration, I will need you to evaluate this integral using that technique, and you might find it much easier. See you on Monday. Homework also due on Monday. Small piece.